Here I am in front of the Smead Aerospace Engineering Department's wind tunnel. The air gets sucked in through this part of the wind tunnel, passes through the test section, which you'll look at more later on, and is blown out on the back side. This is where the fan of the wind tunnel is located. Now, in the interest of being able to show you some of the finer points of the wind tunnel at a closer view, I'm going to use my neighbor's shrink ray to shrink myself down to the size that will fit me inside of this 1 foot by 1 foot test section. Well, that seemed to work well. Hopefully I'll be able to reverse the process. But in the meantime, let's go through the rest of the lab. The first one, to learn basic concepts and definitions associated with wind tunnels and wind tunnel testing. Apply the conservation of mass and Bernoulli's equation to estimate the airspeed. Observe the viscous boundary layer in the test section and understand the implications that it has on articles placed inside the test section in the wind tunnel. Observe how changes of the lift and drag are related to the angle of attack and the free stream velocity. And lastly, develop an awareness of sources of error and uncertainty. Here's a very high-level look at the main objectives of this lab, summarized. Number 1, become familiar with the basic operation of the wind tunnel and testing in general. 2, determine the voltage to airspeed relationship of the wind tunnel itself. 3, observe the boundary layer in the wind tunnel. 4, estimate the lift and drag using the pressure distribution across an airfoil. And finally, 5, apply uncertainty and error analysis and error propagation that you've been learning in ASEN 2012 to this experimental lab. Now, there's a fair amount of content to this lab, so we've put together some interactive presentations which should help you understand the primary concepts. Those interactive presentations can be found on the Canvas page.
Here's a look at the different parts of the tunnel. The flow is from left to right in this view. The room air enters the inlet and then passes to the conditioning stage, also known as the settling chamber. The conditioners include a fine screen to keep out any bugs or things like that, and then a large array of small tubes in a honeycomb orientation to help straighten out the flow. The flow then passes into the contraction section where it is sped up before the test section. In between the test section and the exit is a diffuser section and the fan. The air then exits the tunnel and back into the room. Obtaining an estimate of the flow speed in the test section is a key measurement that must be made in wind tunnel testing. The Smead Aerospace Tunnel has 2 ways to estimate the airspeed in the test section, both of which you'll cover in detail in a lecture in terms of the theoretical aspects and look at more closely throughout this lab. The pedostatic probe uses the difference in the total pressure and the static pressure combined with an estimation of the density to determine the airspeed. The Venturi tube uses the difference in the static pressure in the test section and the static pressure in the settling chamber combined with an estimation of the density to determine the airspeed. Even though these measurements may at first appear to be different, you can see that they are really very similar, if not the same thing, if you recall 2 important pieces of information. 1. The static pressure is essentially the same in the test section everywhere, so the static pressure port at the entrance of the test section gives the same pressure at the static ring on the pedostatic probe. And number 2, the total pressure in the test section is essentially the same as the static pressure of the still air in the settling chamber. You will experimentally determine how the thickness of the boundary layer changes in the test section and what this means about the airspeed estimation of the test section. This image shows the location of the items of the measurement suite of the wind tunnel. These pieces are covered in a lot more detail in the accompanying interactive presentations, so I ask that you refer to that. This image shows the relative location of the pertinent parts of the test section. Again, these aspects are covered in detail in the interactive presentation, so please refer to those as well to improve your understanding of the wind tunnel components.
Now here's a look at the pedostatic probe. You can see here the static rings around the outside of the probe, and then the total pressure port here. Now here I am with the traversing probe that can go upwards vertically in the tunnel, as well as streamwise in the tunnel. This probe is very small, but I myself have been shrunk by my neighbor's shrink ray, so I can do this. I hope that doesn't give the false impression that this probe is very strong. Even though I've been shrunk down, this probe is very fragile, and running the probe into the floor could damage the overall functionality of it. Here's a closer look at the installed airfoil in the tunnel. Whoa, 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 turn it off, turn it off, turn it off, turn it off!
Now that you've seen the different parts of the wind tunnel, let's get to the actual assignment. The wind tunnel fan is controlled by a voltage sent from the operator, the computer, to a fan motor controller. The fan motor controller uses this voltage input to maintain a certain RPM of the fan motor, and hence the fan blades. A higher command voltage corresponds to a higher RPM and a faster airspeed in the test section. You can think of this like depressing the gas pedal on your car. The more you depress the pedal, the faster the engine spins and the faster the car goes. In future wind tunnel experiments, we would like the ability to command an airspeed in the test section and let the computer control the voltage to the fan motor so that we don't have to think about that. This is like the cruise control feature in your car and will make future experiments easier to conduct because you won't have to adjust the fan speed based on the test section article. You will simply let the computer do that work for you. Now, in order for the computer to know how to change the fan voltage based on the test section airspeed, there must be a model to convert fan voltage to airspeed, indicated here with the red block, as well as a calculation to determine an estimate of the airspeed using measurements of the airflow in the test section, indicated here as a blue block. Behind the scenes, a feedback controller uses both of these blocks to constantly adjust the voltage to the fan motor and thus the airspeed in the test section. Now you'll learn more about feedback control in later classes, but essentially all that happens is an estimate of the current airspeed is compared to the desired airspeed, and the fan motor voltage is adjusted to bring that error to zero over time. Now due to COVID constraints, we will post all of last year's data sets instead of taking new sets. Now individuals will have the opportunity to conduct similar tests on the tunnel as desired, but this testing is not required for any groups or any individuals. Now this means you'll be given lots of data files that need to be manipulated using MATLAB to determine specific things like the voltage to velocity relationship or the lift and drag on the airfoil that we'll talk about later on. The ability to write efficient code to load in a lot of data and extract the pertinent information is a valuable skill as an engineer, and one of those skills that you'll be tuning in this lab. Now, a useful MATLAB command for this is the dir command, dir, which produces a struct containing information of all pertinent data files in a directory. The example here uses some quadcopter data from a junior class lab. If you change the number 1 in files parentheses 1.name, the ANS variable, the answer variable, would be the name of the next file in the directory. You can then pass this variable to the load command to automatically load in the next data set. I think you can see if you place a similar structure like this of code into a for loop, you can quickly load in the names and then also the data of all the files. Now, whether you do that all at once or one at a time is up for you and your group to discuss. Personally, I like to load in one data file, crunch all the numbers from that data file, and save the pertinent information before moving on to the next data file. But that code structure is completely up to you and your group. Now, I suggest you use this approach or something similar for your data analysis. Write the code for one data file, calculate the important information, save it somehow, and then put all of that in a for loop that will loop through all of the data files in your directory. Please don't copy and paste the names of individual data files in your code. You'll be given something like 30, 40, 50 different data sets for this lab experiment alone. We need to write intelligent, efficient code. Now you've been exposed to pressures already, and that understanding is absolutely critical to this lab assignment and for your later junior aerodynamics courses. Refer to your textbook and the lecture notes for the precise definition of these pressures. But for this activity, the single most important thing to keep in mind is that the pressure sensors in this lab experiment measure the difference in pressure between the two sides of the transducer, indicated as P1 and P2 in the diagram below. This is very useful for estimating the velocity from the pressure measurements because we know that the dynamic pressure is equal to 1/2 rho v squared. and is also equal to the difference between total pressure and the static pressure, which is what we obtained from the pedostatic probe, the difference in total and static pressures. Now you'll be asked several questions in the quiz that relate to the differential pressures at different parts in the tunnel. This is a critical concept that you must understand to be successful as an aerospace engineering student. The virtual wind tunnel explained on the next slides and in more detail in following discussions should help you solidify this understanding. Now, over the summer of 2020, we developed a MATLAB virtual wind tunnel that should help to give you a sense of operating the SMED Aerospace Engineering wind tunnel without actually touching the wind tunnel controls itself or being in the same room as the wind tunnel. You will be able to configure the different pressure transducers to different simulated connections of the tunnel and observe the corresponding pressure differences. Now, of course, we can't simulate every aspect of the tunnel, namely the sound and the feel of the fast-moving air, but feel free to make your best noises as you see fit. If your roommates, parents, teammates, cat, or dog look at you strangely, just tell them that you are exploring fundamental concepts associated with the differential pressures and wind tunnels, and they will surely understand and let you proceed with your studies. Now, this is a long assignment. I'm not going to break it apart for you like I did in the balloon lab because this is a very important skill that you should work on yourselves. Regardless of how you progress in your career as an engineer, the last two bullet points here are very helpful. One, the ability to not become overwhelmed by a task is accomplished by breaking the task down to manageable chunks. Now, personally, I struggle with this even now, but please trust me, this method works. And number two, this reminds me of the quote attributed to Desmond Tutu. How do you eat an elephant? One bite at a time. Now, I'm not asking you to go out and try to eat an elephant, but this might seem like a giant lab task, so take it one bite, one bit at a time. Lastly, I want to mention that the natural tendency with large assignments is to divide and conquer. Now, I'm not going to fight that tendency, but I will caution you in that you can't really understand an individual part of this assignment without understanding the other parts, namely the concepts associated with pressures, both differential, total, static, and dynamic. We put together the virtual wind tunnel so you can each explore these pressures on your own or in your group. I highly encourage both. Plus, it will help you on your lab quizzes. Now, next time we'll talk about the airfoil measurements of the assignment, and that will be the last technical piece for this assignment.